This video will explain one of the multiple choice questions in the review packets of former questions from previous AP tests. This is in the Riemann Sum packet, and it's number 4, the one I list as an A question, and the one where I say it's perhaps the hardest question in the review packets. By that I mean the hardest multiple choice question, not the hardest question overall. Now, it's a volume question, but that can be misleading because one of the dimensions is 1, is consistently 1 throughout. As soon as you find the area of this shape on this graph, you've answered the question and found the volume. So that's the first thing that's tricky about it. You're not actually finding a volume in the way you do it in other problems. You're really just finding an area. And you need to find this area in the xz plane. X goes from 0 to 2. And z is a function of x given as 1 plus 3x, so it creates this straight line here, starting at 1 and ending at 7. The question is, how do you find this area? Now, that'd be an easy problem, and you don't even need calculus. What you have to do in this problem is recognize the notation they use. So we look at Riemann sums of boxes. Imagine making a sum of right-hand boxes. Okay, we have this box plus that box. Each box gets progressively taller, but they all have the same width, and we call that width delta x. Now we get to choose how many boxes we have, but there's not a specific number in this problem, so we need a letter to represent how many boxes we have, and in this problem they choose the letter n. N means how many boxes you use. Then we have to label each box. See how that's box 1, 2, 3, 4. So this is a number that changes. It's an index that changes by integers by 1 every time, box 1, box 2, and so forth. So we need a number to represent this changing index, and the letter for that is a lowercase I, like I for index. So in their answer, I stands for which box you are talking about, and n is the total number of boxes. So as soon as you say that, you realize, oh, I starts at 1, and it goes 1, I equals 2, I equals 3, I equals 4, and what's the biggest I can ever get? N. So I goes from 1 to n, and that's how these letters are related. All right, so let's see. That's the geometric setup of it, that you're summing a bunch of rectangles, and of course the area of a rectangle is its width times its height. Right, here's that graph again, and here are our boxes, and here's the letter I, right? I equals 1 for that box, I equals 2 for that box, and so forth. And the very last box has I equals n, as we said on the previous board. So now we have two things to deal with, the width and the height. Those two things, and to get them in the notation they use. So what's delta x? See, once you've done this, you actually have too many letters. It's redundant. Some of them are related to others. Some of them depend on others. And so it's now a process of reducing it to the fewest possible letters, reducing it to just I and n, and then the numbers that are given, the actual numerals that are given. So we want to get rid of things like delta x and z and reduce it all to I and n. So first let's look at delta x. How are we going to get rid of delta x? Well, once you have the letter n defined, delta x is just the full width divided by how many boxes you have. That'll be the width, the little length, will be the full width of 2 divided by how many boxes you have. For example, if you have 2 boxes, then each one will have a width of 1, 2 divided by 1. If you had 4 boxes, and you can pause the video and check yourself, if n equals 4, if there are 4 boxes, how wide would each box be? What would delta x be? It would be 0.5, 2 divided by 4. So delta x is a redundant letter. We don't need delta x because we've already got the letter n. So it's the full width divided by the number of boxes. In this particular problem, that's 2 divided by n. In general, if we start at x equals a and ended x equals b, it would be b minus a over n. This would be the general expression for delta x. Here is the one specific to this problem. Okay, so 1 down, 1 to go. We need an expression for the width and an expression for the height of each one. Notice I do the width first because it's easier. It's the same for every box. The height is changing. In this particular problem, it's increasing with every box. So we want an expression for that. We can't just write zi. Okay? We can express it in terms of I and n. We don't have to add another letter, z. So the height is z. And that z is changing, so we write zi. It's different for every box. There's a z1, a z2, a z3. But Here's how we're going to get rid of the letter z. First, we start out with z as a function of x, so we write that. That was given in the problem. X is different for every box, right? X is different for every box, so we have to put a little I here, index. So the height of the first box will be 1 plus 3 times x1. Height of the second box will be 1 plus 3 times x2. Now, two things determine what comes next. First, we pick right-hand boxes. How do you know to pick right-hand boxes? By looking at the answers. You can tell that they're using right-hand box in the correct answer. You may have to play with it a little bit to figure out whether they use right-hand, left-hand, or middle boxes or trapezoids, but it comes pretty quickly. You can see they're using boxes, rectangles, and they're using right-hand boxes. So that, and the second aspect that makes this work out the way it does is we're starting at x equals 0. The initial x, which we call a, is 0. So that means the first value of x will be delta x. There is no initial offset. The very first value of x will be delta x because we're starting at 0. So x1 is delta x. And that means x2, which would be here, is 2 times delta x. x3 would be 3 times delta x. So now we have an expression for xi. It's I times delta x. So see what we've done here? We started needing the height as a z. We got rid of the z because it's a function of x. Then we're getting rid of the x because it's a function of delta x. And there's one last step to go. Okay, so here's a recap. We want the area of each individual box so we can sum them up. Each individual box has a width and a height. We want to express each of these in terms of our letters I and N and the numerals that are given. We started with the width because that's the same for all of them. It's easier. And that's the total width divided by how many boxes. So now we have an expression for the width in this particular problem. Now we're looking at the height. And we started with the idea that z is the height, and it's a function of x. But x is the index I times delta x. All right, as explained on the previous board, this was x. So that means this can be your expression for xi. I times delta x. The index, or which box it is, times delta x. So look what we've got. The height is 1 plus 3 times I delta x. 1 plus 3x. Okay. But we're still not done. No, and I said that correctly, 1 plus 3x, because this is xi, but xi is I times delta x. But we're still not done because this has got a delta x in it. Well, fortunately, in the previous part, we found an expression for delta x, and now we substitute that. So when the smoke clears, you get this. And this is what we wanted, an expression for the height that only has I and N in it. Right? You can see where this comes from. The function for z is 1 plus 3x. Then this is the function for xi. I, the index, or which box it is, times delta x, and then this is delta x, the total length over how many boxes there are, the total width over how many boxes there are. Now, when you put that all together, I don't think I have to talk through this. You can do this just math, arithmetic now. You just put it all together and simplify, and you get that, which is the expression in the correct answer. But you can still see where this comes from. There's the delta x, 2 over n, and this is the height of the boxes. It's getting bigger and bigger each time you advance to I.